Hello everyone and welcome back to the channel. In the early days of big data, before Spark and Flink were household names, there was one paradigm that revolutionized how we process massive data sets, which is MapReduce. While newer technologies have evolved, understanding MapReduce core principle is absolutely foundational for any system designer, and its concept that frequently comes up in system design reviews, especially when discussing batch processing of large data. Today, we are diving into what MapReduce is, how it works, and its enduring legacy. As always, we talk about the problem. So imagine you have petabytes of data, say all web pages on the internet or all the customer transactions for a decade. How do you process this data efficiently? How do you count word frequencies across billions of documents or calculate the average spending per customer across millions? Traditional approach limitations will be we have a single server simply doesn't have enough CPU, RAM, or disk space to handle such massive datasets. Processing would take unacceptably long time or crash the machine. The need for distribution comes after this problem. So we need a way to distribute this enormous workload across a cluster of thousands of community machines, process data in parallel, and then combine the results reliably. This precisely the challenge MapReduce was designed to tackle for batch processing of every large data sets. Okay, let's try to understand how does it work. Or before we talk about how does it work, let's talk about what it is actually. MapReduce is a programming model and an associated execution framework for processing large datasets in a distributed and parallel fashion. As the name implies, it consists of two primary phases, map and reduce. Let's talk about the map. The map is like handling out each book to a different person, which is a mapper, and telling them to list every word they find in their book, along with the count of how many times the word appears in their book. For example, we have cat appeared 2 times, the appeared 5 times, things like that. Number two, we have reduce. Reduce is like collecting all those individual word lists from everyone, from every reducer, and then summing up the counts for each unique word across all the books. So, for example, all the or all cat counts are summed, all dog counts are summed, things like that. This simple yet powerful abstraction allows developer to focus on the logic of what to compute rather than how to distribute and parallelize it. Okay, let's try to understand how does it work. So if you wanna, let's break down, I guess, the execution flow of typical MapReduce job. Number one, we have the input data. Okay, we have large input data files are typically basically stored in distributed file systems like HDFS, okay, or it's Haboot distributed file system. This system will automatically splits the data into smaller chunks and distribute them across many nodes in cluster. Number two, we split the data. Okay, so the map reduce. Okay, the map reduce you have here. This is a reduce. This is a map reduce. The MapReduce framework divides the input data into independent splits, and a mapper task is assigned to each split or a combiner. You can call it that as well. And the and yeah, and after that, the mapper is assigned to each split running on node where the data chunk resides. After that, the mapper function takes a set of input, key value stores or key value pairs, not key value stores, key value pairs, and process them to produce a new set of intermediate key value pairs to framework. Okay, so this is will be. I guess this is one is better, but yeah, this one has more color. I guess has more. Uh, yeah, has more color to it. So yeah, again, the mapper. After that, we will try to split and combine. Okay, and after that, we need to shuffle and sort. This is shuffling and sort. Okay, so again, let's go back. Let's go back. Let's talk about the splitting and mapping, which everything happens here. And as you can see here, everything in key values to value pairs here. I don't know if you can see it here. Okay, so let's try to talk about the split and mapping again, because I guess I didn't talk about it in the best way possible. So again, the MapReduce framework divides the input data. Sorry, the input data into independent splits. After that, a mapper task is assigned to each split, running on the node where that data chunk resides. Okay. After that, the mapper function takes a set of input key value pairs and process them to produce a new set of intermediary key value pairs. Okay. After that, for example, let's say for our word count or whatever it will be, the mapper reads lines of text, for example, break them into words and outputs, for example, word, which is like cat, and how and the occurrences like cat, four, dog, six, things like that. After that, we have here the shuffle and sorting. This is an intermediary phase, intermediate phase. Like after mappers complete their intermediate key value store pair, basically we have three things happening here. First, the key value pairs are partitioned, like all intermediary key value pairs with the same key output are grouped together. These After that, everything will be shuffled. These grouped values are then sent across the network to specific reducer machines that is responsible for that key. After that, we store the key value stores, or the key value pairs, not stores. After that, we store them like within each reducer. The values of for a given key are stored. This ensures that all occurrences of a specific word like cat from all the mappers arrive at the same reducer, grouped and sorted. Number four, we have reduce. A reduce task is assigned to each group of intermediate key value pairs. The reducer function takes a key value pair as input and process this aggregated data to produce a final set of output key value pairs. It will take like not just a key value, it will take like the key out, and it will take all the list values of this specific key, and after that it will aggregate data to produce a final set of output of key value pairs, like final key and final data. For our word count, if we talked again, it will have like we will have something like for example, it will be key value pair, so we will have like something like cat, and we will have all the occurrences. It will be like 1, 3, 4, 5, and yeah, and we can just go to a last one, which will be cat with the total number instead of having an array. So this will be the final output from the reducer, which will be written back to HDFS, usually into a new set files, which is the output here. Okay, it's not that easy to understand. But like you need to understand the combiner, shuffle, and reducer. You need to know it on high level. You don't need to go deep into it. Okay, why MapReduce matters in system design. So, while directly implementing MapReduce jobs has largely been suppressed by faster, more flexible frameworks like Apache Spark or Flink, Spark, not Spark, Spark, understanding MapReduce's principles is still vital for system design. Number one, we have foundation of big data. It introduced the core ideas of distributed batch processing, parallel execution, fault tolerance through task retries, and data locality, which underpin almost all modern big data systems. Number two, scalability. It demonstrated how to scale processing linear by adding more community hardware, making large scale data processing accessible. Number three, fault tolerance. If a mapper or reducer task fails, the framework automatically restarts it in another node, ensuring job completion without manual intervention. Number four, which will be something about interview, I would say interviews will use it to check your understanding of fundamental distributed computing concepts. You might be asked to apply the MapReduce paradigm to a problem. For example, how would you find the top 10 trending hashtag using a MapReduce? Things like that. So yeah, that's it for this video, and yeah, see you in the future.